Hello, geometry students. Welcome to 11.4. We are talking about the three-dimensional object known as spheres here. So I think of probably my favorite sport, basketball, is the sphere that I think about the most in terms of a physical object that I can actually pick up and manipulate and touch to look at. We're going to look at a lot of terminology on this one. The Earth is very, very close to a perfect sphere. I mean, you have some bumps and whatnot, and due to gravity and all kinds of physics stuff that goes beyond my level of understanding. The Earth isn't a completely perfect sphere, but it's about as close as it gets. And in terms of everything out there, yeah, I probably shouldn't get into that sort of discussion. The Earth is not flat, okay? The Earth is a sphere, but yeah, spheres. Let's take a look. So 11.4, this is a chord. So a chord of a sphere. Just look at a chord of a circle. A chord of a circle connects any 2 points of a circle together. A chord of a sphere connects any 2 points of a sphere on the exterior or on the surface of that sphere together. So it connects 2 points on a sphere. So I'm going to put that in parentheses here. A chord connects 2 points on a sphere. And we've got a bunch of other terminology here. Right here is a tangent. So just like we had a tangent of circle was something that just touched the circle at one spot, a tangent of a sphere is going to just touch a sphere at one spot. A pole, just like we have the north and south pole, a pole is going to be one point of a diameter, one end point of a diameter. So this would be another pole over here. So the second pole would be a second endpoint of the same diameter. So endpoint of a diameter is what a pole is. And what else do we have here? This is called a great circle. Great circle. So notice that's this circle right here. It's a circle that contains the center of the sphere that can be drawn there. So the equator is probably the most common example of a great circle on the globe. You could think of the prime meridian as well, or really any longitude lines. If you wrap around through the North and South Pole, would also be great circles. Latitude lines, though, only the equator would be considered a great circle because it's the only one that would contain the center of the sphere. So it contains the center of a sphere. Contains the great circle, contains the center of a sphere. And what else am I missing here? We've got a radius right there. And this would be a diameter going all the way across pole to pole or endpoint to endpoint there and there. And I think that does it for this left picture. And then this one you've heard of, I would assume, or I would hope you've heard of hemispheres before. So you've got the northern and southern hemisphere, the eastern and western hemisphere on the globe. Hemispheres are just going to be half of a sphere. If you sliced it directly in the middle, this would be a great circle right there. It would contain the center of the sphere. Hemispheres are half of a sphere. So the surface area of a sphere and the volume of a sphere, we have two different formulas. The proof of these formulas goes well beyond your standard geometry class. Calculus, pre-calculus, especially calculus, was the first time I saw a proof that I really understood about why these formulas are the way they are. So if you're curious, you want to Google it, see if you understand that proof at the level of math you're at, feel free to go for it. This one it's a lot like if you've ever peeled a baseball or softball apart, this can give you an understanding, or at least an intuitive idea of why this formula works out the way it does. It's 4 pi r squared for this one. So it's 4 circles. If you were to peel the outside of a sphere off, you would end up getting 4 pi r squared. 4 exact circles would make up that's the radius there, would make up the surface area, what would be painted on the outside, so to speak. And then the volume formula is 4/3 pi r cubed. This one definitely takes some higher level math to understand where that's coming from. It does come back to the idea that pyramids are 1/3 base times height, and then it combines that together with the surface area formula. So feel free to dig into that a little bit more if you're interested in knowing the whys behind that, but you just need to know what the formulas are and understand how to use them for the purposes of this class. So we have, for this first one, we're going to find surface area and volume of these solids. So let's start with surface area. You could say just S, capital S if you want to, or SA, and you have 4 pi r squared. This one, all you need is a radius for both surface area and volume. So that's very convenient. Once you have that radius, the formula should be very easy to use from there. So we've got 9 squared on this one. That's going to be 81, and 81 times 4 is going to end up being 324. So we have 324 pi centimeters cubed. We're doing squared. Sorry, we're doing area for this first calculation. So it's 9 centimeters times 9 centimeters. It's centimeters times centimeters for centimeters squared. This would be approximately 1017.9 centimeters squared to the nearest tenth. So exact answer, pi form, approximate answer there. And then volume, 4/3 pi r cubed. So you've got 4/3 pi times 9 cubed. If you cube 9, that's 729, and take that times 4/3, you end up getting 972, and then we have that times pi, so that would be an exact answer here, and this is centimeters times centimeters times centimeters. We're cubing centimeters here, so we're getting centimeters cubed for that. That is approximately 3053.6 to the nearest tenth. So 3053.6 centimeters cubed to the nearest tenth. On this one, if the diameter is 12, the radius, we just divide that by 2, and the radius is going to be 6 meters. So we will use that as our information to plug in. This is, however, a hemisphere. So you may find this useful to write down hemisphere. I mentioned this already. Hemisphere is half a sphere. But when it comes to volume, it's just going to be half of the volume formula. When it comes to surface area, though, the slice that you make exposes a new part of the sphere that wasn't there before. So we would be thinking of this, and I'm gonna write this out the long way first, and then kind of highlight the shortcut formula, so to speak, if you want to use this shortcut formula for surface area. We're getting to that here. So we would be doing 1/2 of what it normally is, 1/2 of 4 pi r squared. That would be this outer part here, but now we have this part showing, and that part from here to here would be a radius. So if you took and looked at that, that would be pi r squared for that extra part that just got exposed. So we have that plus an extra pi r squared now. So this part is a great circle, so that you can see this great circle as part of the area of the surface now. It's exposed. It's something that would have to be painted if you were painting this whole hemisphere. So the great circle is visible. It's a visible part of the surface area in a hemisphere. So it's important that you note that. If you want to use this then as your shortcut formula, you're welcome to. So surface area is going to be half of 4, so that's 2. So 2 pi r squared plus pi r squared. Here's your shortcut formula. There's 3 pi r squared. So surface area is 3 pi r squared. You may want to circle that or highlight that. That is something you're welcome to use as a hemisphere surface area shortcut formula. So then we would plug in 6 in for r, and it looks like we've got 3 times 36 then, which would be 108 pi. So 108 pi meters squared, since it's an area, not a volume. and that's approximately 339.3, and this would be, sorry, I'm writing centimeters again, meters cubed. Squared. That. I'm thinking about volume already. So I'm thinking ahead. Do you ever do that? You're wrapping up a problem or a thought, and you start thinking about your next thought before you conclude that previous thought. And yeah, that happens to me more than I would like to admit. So for the volume, we're taking half of the normal formula. 1/2 of 4/3 pi r cubed. There is no extra part here. There's no extra thing that would be filled up. So if you wanted to use this as a shortcut formula for hemispheres, you'd be welcome to do that as well. So this is a shortcut formula for surface area of hemispheres, shortcut formula for volume of hemispheres. So this would become 2/3 pi times 6 cubed. Come on, pi, there we go. 2/3 pi times 6 cubed. And 6 cubed, 216, 2/3 of 216 is 144. You'd have that pi, and meters cubed, or approximately 452.4 meters cubed. So exact answer here, pi form, approximate answer there. Know how to get both. And then for examples 2, 3, and 4, we're looking at the next page of our note. Next slide has example 2 and 3 on it, given that circle A is a great circle. So we can assume this is the biggest circle you could slice off, in a sense, of the sphere. It's containing a diameter of the sphere. So it has a circumference of 10 pi centimeters, and that should not say squared, so you can cross that out. It's a circumference, it's just a length, so that should just be 10 pi. Oops, there we go. I'm having a little trouble with my pen there. So cross out the squared part there. Sorry about that. So 10 pi centimeters. Find the surface area and volume of this sphere. So circumference, we know, is 2 pi r. Or you could think of it as pi d. So either way. But it would be more convenient to know what r is instead of d, because I'm eventually going to be plugging them into the surface area formula, 4 pi r squared, and the volume formula, 4/3 pi r cubed. So I'm going to figure out, I'm going to use this 2 pi r to figure out what the radius is and go from there. So circumference is given to me as 10 pi centimeters. So I'm going to replace c with 10 pi. So 10 pi would equal 2 pi r. And we could divide by both 2 and pi here. If you're going to use a calculator to do this, I think you're making an unnecessarily hard. You can just cross out the pi's, and then 10 divided by 2 is 5. If you were using a calculator, be careful, use parentheses around the 2 pi, otherwise it's going to divide by 2 and then multiply that by pi. According to PEMDAS rules, that's how it would work. So 5 equals r for your radius. We're going to take that now and plug it into both formulas. We've got 4 pi times 5 squared. 5 squared is 25, times 4 is 100. We've got 100 pi. And units on this one would be centimeters squared for an area, or 314.2 centimeters squared rounded off to the nearest tenth. And then take your radius of 5, plug it into the volume formula to get the other one. This would be 125 times 4 would be 600, divided by 3 would be 200. So we would have, or what am I saying here? I'm sorry, 5 cubed would be 125 times 4 would be 500. There we go, divided by 3 does not work out nicely. So you'd have 500 divided by 3 times pi, or in other words, 500 pi over 3. And that would be in centimeters cubed, and that's approximately, to the nearest tenth, 523.6 centimeters cubed. For example 3, given that circle C is a great circle, so it's containing a diameter, and half of that would be the radius. The area here is 40 inches squared. Find the surface area and volume of the sphere. So the area of this great circle right here would be pi r squared. And the area is known. It's a known quantity right here, 40 inches squared. So you can replace A with 40. There's no pi included in this one, so we will be dividing by pi. The pi wouldn't cancel with anything on the left side, but it would cancel here with that. There we go. And so you'd have 40 pi over pi equals r squared. Then you can take the square root of both sides to get your answer for r. So I'm going to leave it like this for now. R is exactly the square root of 40 over pi in this problem. And I'm going to take that and plug it in. We're trying to find surface area and volume on this one. So I'm going to use my calculator to do the grunt work for me here. Boy, before calculators, something like the square root of 40 divided by pi, to get that to any level of decent, accurate approximation would have been very tedious. But calculators, very thankful for those these days. You plug that in and take that. This would cancel. So square root and square would cancel. You'd be left with, you could do this without a calculator. So we'd have 4 times 40 would be 160. And then that times pi on the top. And then this is like this over 1. So you have 4 pi times 40, 160 pi. 1 times pi on the bottom, pi. The pi's would cancel. And you'd be left with just 160 exactly inches squared for that one. And then for surface area and volume, so for the volume, 4/3 pi r cubed would become 4/3 pi times, and then on this one, we're taking the square root of something, but then we're cubing that, so there's not going to be a nice cancellation like there was over here. This one definitely going to want to use a calculator for that. So that's 40 over pi, square root of that, cubed. Use the calculator to approximate what that is from there. So this one would be about 190.3 inches cubed since it is a volume. Careful with those units. Surface area squared, volume cubed. Finally, example 4. We are looking at a sphere that has a volume of 500 meters cubed. So the volume formula, 4/3 pi r cubed, should be useful, or should be what we would need to use to figure out what's the radius. If we're going to try to find the circumference, we'll need to find either the radius or diameter. The radius would be directly given to me using this formula, and I could take that, plug it into there to get the circumference for that great sphere. So at this point, replace V with 500. You have 4/3 pi r cubed. You're definitely going to need your calculator for this one. Make sure you have the knowledge of where this button is or how you would do this calculation on your calculator. So here we're trying to get r by itself. So we're trying to get rid of this 4/3 pi multiplied by that. So you could think of this as divided by 4/3 pi. And then from here, I think using a good approximation would be okay, but I think even better would be to keep it exact as long as possible. So you could do it this way. That's one way to do it. I think I'm going to backtrack though. So if you want to go that route with it, go ahead and do that. But if you instead, to make things a little easier to deal with fraction-wise, I can multiply by the reciprocal. Dividing by 4/3 is the same as multiplying by 3/4. If I do that on that side, I have to do that on this side. So if I multiply 4/3 times 3/4, they cancel. It's just 1. And if I multiply this out, 1,500 on the top divided by 4 ends up being 375. So I've got exactly 375 would be pi r cubed. Then I could divide both sides by pi. And what I had written initially would do the same thing for you, but I like this form better myself. This, instead of getting a rounded off decimal, that would become even worse of an answer or even have more of a rounding error if we round off too early or too soon in the middle of a problem. This is going to give me the best exact answer. So you're going to need to find the cube root button on your calculator. We're not taking the square root of that because that's not going to cancel with that. So we're looking for the cube root of this side and the cube root of this side. What times itself 3 times gives you that value under the cube root. So on some calculators, I'm going to do some work off to the side here in black here. So if you type in parentheses 375 divided by pi, and then find the caret button, raise it to the 1/3 power, that's the same as taking the cube root. You're welcome to do that. I think that's probably the way that would work for the most people. There is a cube root button on many calculators. It would look like that, or you might even find something that has like a variable that you could fill in there. These sorts of buttons would be just fine to use. So this is kind of a side note down here. Look for this on your calculator, something like that. It's not the square root though. If you take the square root, you will not get the right value. The cube root of 375 divided by pi ends up being, well, I could write it, leave an exact like this, the cube root of 375 over pi. I'm not done with this is not a final answer. So if I'm going to round, I want to use just a personal preference of mine, 5 or more decimal places. If you go too short and then you're going to multiply it by something else, it will just expand upon that rounding error. We won't get into significant digits here, but you could get into that conversation too if you wanted to. So this is the nearest 5 decimal places. What is that, 100,000th, I think, tenths, hundreds, thousands, 10,000, hundreds, thousands, yeah. We have that as our value. So I'm going to plug in 2 pi, and then I'm going to use the exact value here when I write it down, but you could plug that in here as well, and you should get an answer that's acceptable for the purposes of what we're doing here. So the cube root of 375 over pi, multiplying that by 2 pi, rounding that off, ends up giving you to the nearest tenth 30.9 meters. And this is circumference, so it's just a length. It's the length around that great circle. So it's just meters, not meters squared, not meters cubed. That does it for 11.4. Hope you found that useful. Hope you found that button on your calculator. If you're one of my students and are having trouble with that, send me an email, or any students out there watching this on the wonderful world of YouTube, feel free to comment on the video and I can try to help you further with that. Besides that, hope you found it useful. Hope you find some practical uses for this kind of stuff in your life at some point, and hope you have a great day.